So, learning goal, we're going to recognise and determine features of the graphs of y equals x cubed, y equals a outside of x minus b, or cubed plus c, and in particular the main focus will be on y equals k outside of x minus a, x minus b, x minus c, and in fact the first two were pretty much taken care of in a previous video. We'll be alluding to them occasionally only, mainly the third one in yellow. We'll look at the shape, we'll look at the intercepts, the behaviour as x gets very big and very small. Okay, so that's why we say as x approaches infinity or as x approaches negative infinity. You'll hear more and more about that as we go through. So previously, in the previous video, for the graph of a cubic in that form, it had a point of inflection hk, is one of the most recent things we learned. There's other things to know. So with the features, we'll have a look at an example, and we've got that form that we just saw up above, the third form in yellow, where k equals 1. So we've got three factors here. Okay, so that's factorized form of a cubic. We have three factors, and we want to do a basic sketch of the graph. Turning points is something that we're going to look at in the future, especially once we eventually get to calculus, but we're going to omit that now or farm it out to technology, but we'll learn a mathematical way of dealing with that in the future. So stay tuned further into the future, but we can use technology to find those turning points. If you're a massively impatient person, learn about the derivative and learn about when the derivative equals 0, and you'll be able to work out turning points more or less, but that's further into the future. So basically we can look at some key points. We can look at the X-Intercepts, and that's when y equals 0. So we're setting everything equal to 0, and it's really null factor law, and null factor law you can see in play there, and that gives us our X-Intercepts. That's from previous work, that concept. Y-intercept, as you know, is when x equals 0, and basically we sub in x equals 0 and the y-intercept is -2. We're only expecting one of those, aren't we? So at the moment we've got 4 points. That's pretty handy. Now what we need to do is, this will be eventually called a sign diagram. We'll draw a diagram of this, but not yet. Sign diagram is coming up, but not in this video. We need to do some work with division of polynomials and so on before we do that. However, we are going to look at the sign, as in, is it positive or negative, over certain intervals, over certain sections of x. So when x is greater than 1, so that's there, y is greater than 0, and if you look at the function, it's going to keep getting bigger and bigger. So we could say that also as x approaches infinity, y is not only positive, but y would approach infinity as well. Okay, we can see that because of the nature of the function. If you kept subbing in bigger and bigger values, why don't you pause the video and try that yourself? Sub in increasingly larger values of x, and you'll get increasingly larger values for y. Obviously you can't substitute infinity into your calculator, as you know. Don't get me started on that, but just sub in really large values for x and see what happens, and make in some even larger values for x and see what happens. Okay, so when we're looking at the next interval, between -2 and 1, so we're back over here again. So we were there, now we're back over here. You can sub some values in and look at the nature of the function, and you know that it's going to always be positive there. When x is between -1 and 1, y will always be negative. When x is less than -2, so that's going out that way, y will be negative. So as x approaches negative infinity, because we're going to the negative end. Y, you can again sub in larger negative values, if that makes sense, more negative numbers, and numbers that have a big magnitude but a negative sign on them, bigger and bigger. Y will approach negative infinity. Now that's not always the case on functions, but you'll notice the shape, it'll swing down and it'll swing up, and that corresponds with that and that. And when we get into curve sketching using the derivative, again that's further into the future, we will use these concepts again too, so it's important. Some things don't curve down and curve up at the ends, so they're called the endpoints. Now that relates a little bit to what's written here at the bottom. Beyond the intercepts, so you can see that again that's there and there, that same section that we were just talking about. As x, for x is greater than 1, y is greater than 0, and as x increases, y increases. That's a very similar statement to that. And as x decreases, y decreases once you get past that intercept, i.e. here. That's pretty much the same as that. Okay, so moving on to the next one now. The graph of the cubic function here is a reflection of the one we saw above. So if you look at the one of this is because if we expanded that, we would get that there, and we have a reflection because all of the terms are multiplied by -1. In other words, the whole equation is multiplied by -1. So you can see the link there. All the signs of all the terms change, so it's a reflection in the x-axis. That shouldn't be a huge surprise, because we know that when we have a dilation of -1, that's what that does, it reflects everything. And so your characteristics, a lot of them reflect, but you'll notice that the zeros are the same. So the x-intercepts, in other words, are the same, but the y-intercept is different. X-intercepts are the same, y-intercept is different. It's the opposite sign but the same size. So 2 versus -2. We've got the regions now as x. There are some differences there. So between the zeros, we've got, let me declutter this. So I was saying between the zeros, on the mirrored one we have the value here between these two zeros, x equals -2 and 1, we have a negative value for y, but if we look back up here it's positive. And between these zeros here, the value is negative for y and the value is positive for y. Okay, so those things are mirrored. The behavior, as we remember, the behavior here as x approached -infinity, so did y on this one. As x approaches -infinity, what does y approach? Y approaches positive infinity. Interesting. So, and this one here, as x approaches positive infinity, y approaches negative infinity. Let's compare that with the above. Alright, opposite. Interesting. So that just shows you the effect of a reflection. Now cubic polynomials, how many zeros or how many x-intercepts can they have? Well, let's look at an easier example with the quadratics. Let's go back. Quadratics, we know about them. Quadratics, how many zeros? Now think about the discriminant. How many zeros or solutions can we have, or x-intercepts? We can have up to 2, but some only have 1, and some have none at all. So it can have 2, 0, 1. With the cubics, it can have 3 zeros, 2 zeros, 1 0, or none. And sometimes a reduced number of, reduced from 3 that is, a reduced number of factors or zeros is due to what's called repeated factors. You see, hopefully you've worked out with polynomials, the number of factors has a direct relationship with the number of zeros. So factors, zeros, x-intercepts, solutions, roots, all the same. So looking at this one here, is a cubic because we have a squared and a to the 1, and if you expanded that out, your leading term would be x cubed. So that is a cubic there. You may need to pause the video to have a closer look, or even expand it yourself and test it out. But that's a cubic, and it has a repeated factor because if you expanded the first factor out, you could write x minus 1, x minus 1, and then x plus 3. Now that is going to give the same x-intercept as that when it's set equal to 0. So you can see that x equals 1 will be one of the zeros from our previous work, and it can only go through there once, can't it? And well, actually I was pointing to the diagram for this one, I should say. Sorry, my mistake, pointing to the wrong diagram. That one there would have basically this graph here. I'm pointing to the correct graph now, and so the x minus 1 will only produce 1, even though it's 2 factors, it's the same factor 2 times, so it's only going to produce 1 0, which is that one there, 1 comma 0, and the other one will be x plus 3. So that's only got 2 factors, or 2 x-intercepts, 2 solutions. Remember, we solve when it's in factorized form and equal to 0. That's the solutions, that's the x-intercepts from our previous work. So with this other example, which I made a false start on before, we've got 2 factors. Y will equal 0 when x equals 0, because when x squared, that x squared term, when you sub in x equals 0, it'll create 0. So there's 1, and then when x equals 1 there, you can see. So it'll only have, it has a repeated factor, that one, and it'll only produce x equals 0 and x equals 1. So, and it's also, this one here is also the y-intercept as well. And as we said, some cubics only have 1 x-intercept, and all of these ones in this form do. They have a factor that repeats 3 times, so the all cubed type quadratics. But some other ones do as well. If we look at this one, it's only got 1 x-intercept, or 1 factor. So basically that comes from the fact that if this one could be factorized into 2 factors, it would give 1, 2 of the factors, and this would give the 3rd factor here. So you'd have 1 and then 2, 3. But this quadratic factor, if we apply the discriminant on there from our work on quadratics, it cannot be factorized further. So there are no, remember when the discriminant is less than 0, there are no factors, so it only comes from that one. So when x equals 1, we have our factor generated. Of course, we can find our y-intercept by making x equals 0, and we get 5. So a summary, basically, let's quickly go through. So the graph of a cubic, we can have 1, 2, or 3 x-intercepts. Cubic can be written, if it can be written in that form, then what you do is to graph it or find its key features, you find the x-intercept, you find the y-intercept, you find the x-intercepts. Now I said we'd go through the sign diagram thing soon, but you analyze the signs. Okay, so like we did, analyze the signs in each of the intervals. That's like towards the beginning of this video. Okay, and then we look at the endpoints. Consider the x values as x increases to the right of all the x-axis. They're called the endpoints, and the endpoints at the other end. And consider what happens as x approaches positive infinity and as x approaches negative infinity. What happens to y? Y approaches what? Y approaches what? And also at the endpoints, we're looking at the sign. Once it's gone past the x and the x-intercepts on both sides, on the right and the left, is it positive? Is it negative? That's what we saw earlier in the video. Lastly, for repeated factors, if there is a repeated factor to the power 2, the y values have the same sign immediately to the left or right of the corresponding x-intercept. So we looked at the repeated factors, in other words,